calculate the charge on a peptide at a given pH, the first thing you need to know is which side chains are ionizable. Here's a list of ionizable side chains. You have acidic and basic side chains. There are 4 acidic side chains in which the proton can be lost to yield a negatively charged conjugate base. And there are 3 basic side chains which can take protons from the solution to yield a positively charged conjugate acid. The reaction equilibrium for acidic side chains is included here. So here you have the generic form of the acid, which you can label as HA. The proton can be lost to the solution, yielding a negatively charged conjugate base. On the contrary, if I draw a similar equilibrium for basic side chains, here on the left, I have the protonated form. So this I can just label as a generic BH, but it has a positive charge. Notice the BH has a positive charge. Still, the proton can be lost to solution, yielding a neutral equivalent of the basic side chain, which has 0 charge. Knowing the pKa of the side chain, you can determine the protonation state of an individual molecule of acid or base. At a pH that is less than the pKa of the side chain, the group will be protonated. At a pH that is greater than the pKa of the side chain, the group will be deprotonated. So at pH greater than pKa, the group is deprotonated. At pH is less than pKa, the group is protonated. I'll write that down. So when pH is greater than pKa, the group is deprotonated. And at pH is less than pKa, the group is protonated. This is true for both acidic and basic side chains. The only difference is when deprotonated, the acidic side chains form a negatively charged conjugate base. On the contrary, when protonated, the basic side chains form a positively charged conjugate acid. Here, this little table lists the protonation states under different conditions. So when pH is less than pKa for acidic side chains, the group is going to be predominantly protonated, and the net charge will be 0. When pH equals pKa, the concentration of the protonated and deprotonated forms will be equal. And when pH is greater than pKa, the concentration of the deprotonated negatively charged form will predominate. In contrast, for basic side chains, when pH is less than pKa, the protonated positively charged form will predominate. When pH is equal to pKa, the concentration of the protonated and deprotonated forms will be equal. And when pH is greater than pKa, the deprotonated neutral form will be the predominant species in the solution. The 4 amino acids with groups that can behave as acidic side chains include aspartate, glutamate, cysteine, and tyrosine. Aspartate and glutamate are usually always deprotonated at biological pH. Tyrosine will generally be protonated at biological pH. However, under specific conditions, it may be deprotonated. Cysteine may be deprotonated at biological pH. However, remember cysteine is typically oxidized to form disulfide bonds. However, it can exist in a deprotonated state. Among the basic side chains, lysine and arginine will generally always be protonated and positively charged at biological pH. Histidine may vary in protonation state depending on the exact conditions. It tends to favor the deprotonated state, the deprotonated neutral state, at pH of 7.2 to 7.4. However, histidine's pKa makes it very versatile in terms of protonation state, and it is very responsive to acute changes in pH. The pKa's for each of these amino acid side chains are listed here. There are also two groups at the terminal ends of any peptide, and these include the N-terminus and the C-terminus. The pKa of the N-terminus, I'll put them here, so NT and CT. So the pKa of the N-terminal group is around 9 to 10. I'm going to estimate around 9. For the C-terminal group, the pKa is around 2 to 3. We'll estimate around 2. This is for the N-terminal amine on the main chain. And this is for the C-terminal carboxylic acid, which I'm going to abbreviate Ca. The first thing you need to do in determining the approximate charge on a peptide is to identify the amino acids with ionizable side chains, and then to determine if the pH given is greater than or less than the pKa. One mistake that students often make is that they forget to account for the N-terminal and C-terminal ionizable groups. And so one thing you might want to do whenever you first start is to just draw them in. Now, go down the peptide chain and identify if the pH is greater than, less than, or equal to the pKa. For the amino group, the pH is less than the pKa. For tyrosine, the pH is less than the pKa if we're using this pH of 7. For valine, valine does not have an ionizable side chain, so it will not change in charge state depending on pH. Aspartate, the pH is greater than the pKa. Alanine is like valine, it does not have an ionizable side chain. Similarly, glycine does not have an ionizable side chain. Lysine does. However, its pKa is greater than the pH. Cystine's pKa is greater than the pH. Arginine's pKa is greater than the pH. And the C-terminal group's pH, or pKa, is greater than or less than the pH. So the C-terminal group's pKa is less than the pH. The charge is going to differ for each of these, depending on whether or not they are protonated or deprotonated, and also depending on whether or not they are acidic or basic. Recall that basic groups, when deprotonated, are neutral, but when protonated, are positively charged. Acidic groups, when protonated, are neutral, and when deprotonated, are negatively charged. The N-terminal group is basic. Tyrosine is acidic. Aspartate is acidic. Lysine is basic. Cysteine is acidic. Arginine is basic. And the C-terminal group is acidic. For my N-terminal group, the pKa is greater than the pH, and therefore it will be protonated, and therefore it will have a positive charge. For tyrosine, the pKa is greater than the pH, but it is an acidic group. Therefore, it will be protonated and have a neutral charge. So no charge. Aspartate is acidic. Its pKa is less than the pH, and therefore it will be negatively charged at pH 7. Lysine's pKa is greater than the pH. It is basic, so it will be positively charged. Cysteine has a pKa that is greater than the pH. It is acidic, so it will be neutral at pH 7. Arginine's pKa is greater than the pH of 7, and therefore it will be positively charged since it is basic. And the C-terminal main chain group has a pKa that is less than the pH. It is acidic, so it will be negatively charged. Now, to determine the net charge on the peptide under these conditions, you just add up the number of positive charges and subtract from that the number of negative charges. So I have 1, 2, 3 positive charges, and then 2 negative charges. 3 minus 2 gives me a net charge of positive 1. So at a pH of 7, this peptide given has a charge of positive 1. Let's do the same calculation at a pH of 1. So at a pH of 1, this is at the extremes of pH. Pretty much every single group is going to have a pKa that is greater than this pH. And therefore, all of them will be protonated. So you can go in here and just say that the pKa is greater than the pH for all of these ionizable side chains and the ionizable main chain groups. And since they are protonated, the basic groups will have a positive charge, so you can go in and just give a positive charge to all the basic groups. And the acidic groups will be neutral. Now, same thing, you just need to add the number of positive charges and subtract the number of negative charges. Number of positive charges are 1, 2, 3, but there are no negative charges, and therefore, the net charge on this peptide at pH of 1 will be positive 3. Let's calculate the net charge on the peptide at pH 12. pH 12 is another extreme of pH. Most of the groups are going to have side chain pKa's, or including the main chain, they're going to have pKa's that are less than the pH. However, arginine is the exception. So arginine's pKa is 12.4, and therefore its pKa will still be greater than the pH at pH 12. But here I can go in and I can say that the pH is greater than the pKa for the N-terminal group, for tyrosine, for aspartate, for lysine, for cysteine, not for arginine, but it is greater for the C-terminal carboxylic acid group. Since the pH is greater than the pKa for most of these groups are going to be deprotonated. And since they are deprotonated, the basic groups will have a 0 charge, and the acidic groups will have a minus charge. So here, my basic groups when deprotonated are going to have a net 0 charge. 0 here. However, recall that arginine will not be deprotonated. Arginine will be protonated since its pKa is greater than the pH, and therefore it will retain its positive charge. The acidic groups, when deprotonated, will have a net negative charge. So tyrosine, aspartate, cysteine, and the main chain carboxylate group will all have net negative charges at a pH of 12. Now, count the number of positive charges. There's only one positive charge. And subtract the number of negative charges. There are 1, 2, 3, 4 negative charges. So 1 minus 4 gives the peptide a net charge of minus 3 at pH of 12. Let's do one more example at an intermediate pH. Let's say that the pH is 8.5. So at a pH of 8.5, if I just label the pKa's up here, might be helpful just to see whether or not they are greater than or less than the given pH. So here, recall, this is about 9. For tyrosine, it's 10.1. For aspartate, it's 3.8. For lysine, it's 10.7. For cysteine, it's 8. For arginine, it's 12.4. And for the C-terminal group, it's going to be about 2. At a pH of 8.5, the N-terminal group has a pKa that is greater than the pH. So I've indicated these with greater than or less than signs. This is how I do it. However, you may find it more useful just to indicate whether or not the group is protonated. And you can just write P for protonated or D for deprotonated. Here, since the pH is less than the pKa, the N-terminal group, the N-terminal amine, will be predominantly protonated at this pH. Since tyrosine has a pKa greater than the pH, it will also be predominantly protonated. Aspartate, however, will be deprotonated. Lysine will be protonated, since its pKa is greater than the given pH. Cysteine will be deprotonated. Arginine will be protonated. And the C-terminal carboxylate will be deprotonated. Since the N-terminal amine will be protonated, it is a base, it will have a net positive charge. Tyrosine will also be protonated, but since it is an acidic group, it will have a net 0 charge. Aspartate will be deprotonated. It is an acidic group, and it will have a net negative charge. Lysine will be protonated. It is a basic group, so it will have a net positive charge. Cysteine is an acidic group and will be net deprotonated, so it will have a net negative charge. Arginine will be protonated, and it is a basic group, so it will have a net positive charge. And the C-terminal carboxylate will be net deprotonated, and therefore it will have a net negative charge. Once again, I'll just add up the number of positive charges and subtract from that the number of negative charges. I have 1, 2, 3 positive charges, minus 1, 2, 3 negative charges. And so at a pH of 8.5, my peptide will have a net charge of 0.